Inverse trigonometric functions. In a trigonometry class, you should have learned about the inverse trigonometric functions. In this course, we will learn how to calculate the derivatives of those functions and how we can work with them from that point of view. So from trigonometry, remember that the sine, cosine, and tangent functions were all periodic functions, and we learned how to create how to change each of those functions so that they would have an inverse by limiting the domain. We created the inverse function for each of them, and we have the notation for them. So we have, for example, y equals sine inverse x. So remember that when we have this notation, that's an inverse, not an exponent. And we have the other notation, arc sine x, and we have the domain and range for each of these, and the cancellation formulas. Sine inverse of sine x is x, as long as x is between negative pi over 2 and pi over 2, and sine of sine inverse of x is x, as long as x is between negative 1 and 1. And these have to do with the domains and ranges of the two functions, the sine and the arc sine. And we have a similar breakdown of the arc cosine and the arc tangent. All right, so if we are asked to evaluate sine of sine inverse of negative 1/2, well, we could just directly say that this is equal to negative 1/2 since negative 1/2 is between negative 1 and 1. Now, if you want a little bit more detail, what we learn in trigonometry is that sine inverse of negative 1/2, one way we can think of it is, what angle between negative pi over 2 and pi over 2 has sine negative 1/2? And so you would draw a reference triangle, and the references would have a negative 1 here and the 2 here, and this is a reference angle. And completing the right triangle, we have a root 3 here, and we know that this is a special angle, and this angle here is negative pi over 6. So if I call this angle x, then x is equal to negative pi over 6. And so then this becomes the sine of negative pi over 6, which is negative 1/2. In exercise B, we're asked to evaluate sine inverse of sine of 5 pi over 6. And it's very tempting to write 5 pi over 6. But that's not correct. And this is not correct because, so this is not 5 pi over 6 since 5 pi over 6 is greater than pi over 2. And pi over 2, it's outside the range of the arc sine, the sine inverse function. And so this is not correct. Alright, so what is the correct approach? Well, I can evaluate the sine of 5 pi over 6. The sine of 5 pi over 6, what's the sine of 5 pi over 6? Would be, here's 5 pi over 6. My reference angle here is pi over 6. And so I would have a 1, a root 3, and a 2. So the sine of 5 pi over 6 is positive 1/2. So sine inverse of sine of 5 pi over 6 is equal to the sine inverse of 1/2. Now the sine inverse of 1/2, for sine inverse, we have to think of the angle between negative pi over 2 and pi over 2. So now I can draw this reference angle. And my reference angle is pi over 6. And so this would then equal pi over 6. Okay, so we have to be careful sometimes when we're evaluating these expressions. Now, what if we were asked to evaluate or simplify the expression cosecant of arc cosine of 3/5? All right, so what we generally do here is we say, well, I'm going to think of this arc cosine as an angle. I'm going to think of the arc cosine of 3/5 as some angle measure. And so what I do is I draw an angle whose cosine is 3/5. And since it's the arc cosine, it's got to be in either the first or the second quadrant. I know the cosine is positive in the first quadrant, so I draw a first quadrant reference with cosine 3/5. So there's my theta, and the cosine, that's adjacent over hypotenuse, is 3/5. Solving the right triangle, I can find that the remaining side measures 4 units. So now I evaluate the cosecant of that reference angle. And recalling that cosecant of an angle, we can think of, in terms of a triangle, we can think of it as the hypotenuse over the opposite. And so then the cosecant of arc cosine of 3/5 would be 5/4. What if we were asked to evaluate the tangent of sine inverse x? Well, again, I would say, well, let me call this some angle. I'll call it, again, theta. Now, the way the arc sine works, this could be, if x is positive, then I have an angle in the first quadrant, and if x is negative, I have an angle and I always call it the negative first quadrant in this context. So, I could actually have two triangles, two reference triangles. I could have one here, where this is my theta, or I could have this triangle here, where this is my theta. Now, in either case, we need the sine to be 1. So for the sine to be 1, remember, we need the sine to be x. And so I'm going to think of that x as an x over 1. And so for the sine to be x, or x over 1, that's an opposite over hypotenuse. So I can have the x here and the 1 here. Opposite over hypotenuse. Or if my x is negative, then I would have the x and the 1 on those respective positions. Now, in either case, I would need to solve for the remaining piece, the remaining leg of the triangle. And notice that that leg of the triangle is the same quantity no matter which triangle we're looking at. So then, applying the Pythagorean theorem, let me just call this momentarily, I'm going to call this box. I know that box square plus x squared would equal 1 squared from the Pythagorean theorem. So then box squared would equal 1 minus x squared, and so box would equal, now if I'm going to be careful here, I should really say plus or minus the square root of 1 minus x squared. But looking at its position in our coordinate system, that value would have to be positive, right? That distance from the origin is a positive. And so I'll call box just the square root of 1 minus x squared. And now evaluating the tangent of that angle, the tangent being the opposite over the adjacent, I would have x over the square root of 1 minus x squared. All right, so those were some examples of how we can work with the inverse trigonometric functions. We're going to need to use some of these ideas in just a moment. All right, so now let's start looking at the calculus. We want to differentiate y equals sine inverse of x. All right, so remember that what this implies is that x on domain -1 to 1, and y, the range, is going to be on -pi/2 to pi/2. All right, so if we keep that in mind, we want to find dy dx. Right, so we want dy dx. Now, we don't have a formula for this yet. So we're going to develop the formula, and we will do that. I'm going to do that by using the fact that sine inverse is an inverse. And so if y equals sine inverse x, then I can write that the sine of y is x. And I'm going to apply the d by dx differential to both sides of this equation. D by dx of sine y, well, that would be the derivative of sine, so that's cosine, leave the inside alone, and then chain rule d by dx of the inside. Right hand side, d by dx of x is simply 1. And so now I have cosine y times dy dx is equal to 1. So then I can solve for dy dx. dy dx is equal to 1 over cosine y. Well, now wait a second. Cosine y, from the very beginning, we said that y was sine inverse x. That's what we started with. So dy dx is equal to 1 over the cosine of sine inverse x. Now wait a second, that sounds sort of familiar. We just did an exercise sort of like that in the previous slide, where we had to evaluate tangent of sine inverse x. Now it's just a cosine. So if we took that same diagram that we had just a moment ago, there's our coordinate system, and I drew these triangles, and I thought of this as a theta or this as a theta, and I had the x and the 1 here, and we solved for the remaining side of the triangle, and the remaining side of the triangle ended up being 1 minus the square root of 1 minus x squared. So then what's the cosine of that angle theta? That doesn't matter which theta we look at, the cosine is the adjacent over the hypotenuse, which would be 1 minus x squared over 1. And so then what we find then is that dy dx is 1 over the square root of 1 minus x squared. This gives us the derivative of the sine inverse. So now would be a good time to pause and maybe try this one on your own, and to differentiate y equals tangent inverse x using a similar technique. All right, so using the same ideas, I can write then that tangent y is equal to x. I apply the differential with respect to x to both sides of the equation. The derivative with respect to x of tangent y, that would be secant squared y times dy dx. And dy dx of x is 1. Alright, so now, dividing through by secant squared y, then dy dx would be 1 over secant squared y. Oh, wait a second, 1 over secant, that's the same as cosine. So dy dx would equal cosine squared y. So then dy dx would equal cosine of y. Well, wait, y was tangent inverse x, and then I would need to square that whole thing. All right, now, we use that same diagram idea. If y equals tangent inverse x, so I would have now tangent inverse. That gives me, again, an angle on negative pi over 2 to pi over 2. All right, so remember, for tangent inverse, we have x. X can be any number. And y is between negative pi over 2 and pi over 2. So again, I would have these two triangles. And if I call this my theta, or y actually, I could call it in this case. Now, since it's tangent, that's I'm going to think of opposite over adjacent. So I would have the x here, and I would have the 1 there. That would be the adjacent side to the angle. So now, solving for the hypotenuse, I would have that hypotenuse square. I'll just use c. C squared would equal 1 squared plus x squared. And so c would then be the square root of 1 plus x squared. Then the cosine of tangent inverse x would be, cosine is adjacent over hypotenuse, would be 1 over the square root of 1 plus x squared. And so then dy dx would be 1 over the square root of 1 plus x squared, and that whole thing squared. So then dy dx would be 1 over 1 plus x squared. So if we had the tangent inverse function, its derivative is 1 over 1 plus x squared. So for reference, here's a listing of the derivatives of the inverse trigonometric functions. You should memorize these three, the derivatives of the arcsine, the arccosine, and the arctangent. They're the ones that we use most often. Find the derivative of the function, simplify where possible, and we have y is equal to arcsine of x to the fourth. Alright, so the derivative of the sine, arcsine, the derivative of arcsine is 1 over the square root of 1 minus, now I'm not going to use x, I'm going to use u. I want to use u instead of x here. Alright, so because now in the place of u is x to the fourth. And then we'll have a du. Alright, so then y prime would be 1 over the square root of 1 minus x to the fourth squared, and then times a d by dx of x to the fourth. So then y prime would be d by dx of x to the fourth. That's going to end up in the numerator, so that's a 4x cubed, and in the denominator, square root of 1 minus x to the 8th. Alright, why don't you try the second one? That would be a good time to pause. Alright, so if y is equal to arcsine of 2x minus 1, then y prime would be equal to 1 over the square root of 1 minus 2x minus 1 squared times d by dx of 2x minus 1, which is 2. So then y prime would be 2 over the square root of 1 minus 1, 2x minus 1 squared. So we often wouldn't see it like that. Let's see how we can simplify this. Now 2x minus 1 squared, using what we've learned in algebra, that's a 4x squared minus 4x plus 1. So then y prime would be 2 over the square root, and now simplifying this, I would have a negative 4x squared and a plus 4x. Notice that these remaining terms have a common factor of 4. And so I could write this as y prime is equal to 2 over the square root of 4 times, and I'm going to switch the order of the terms, x minus x squared. Using, again, what we learned in algebra, y prime would be 2 over the square root of 4 times the square root of x minus x squared. And notice that the square root of 4 is 2, and so that removes that term, that factor from the numerator. And so y prime in simplified form is 1 over the square root of x minus x squared. If f of x is equal to arc cosine x divided by x, I'm going to use the quotient rule here. So then f prime of x would be low d high. Alright, so the derivative of cosine inverse x is the same as the derivative of sine inverse x, is negative. So negative 1 over the square root of 1 minus x squared minus high d low, cosine inverse x times the derivative of x is 1, and that's over x squared. Now recall that we often don't like to have fractions within a fraction, so we would many times see this simplified through a multiplication in both the numerator and denominator. So I'm going to say we have that fraction, I'm going to multiply both the numerator and denominator by the square root of 1 minus x squared. And so then I can write that f prime of x would be negative x minus cosine inverse x times the square root of 1 minus x squared over x squared times the square root of 1 minus x squared. And so here is a quote-unquote simplified form. Here's another good one for you to try. If h of x is x times arctangent x, calculate its derivative. Right, so then h prime of x, using the product rule, would be x times the derivative of tangent inverse is 1 over 1 plus x squared plus the derivative of x is 1 times the arctangent of x. And so we might just write this as x over 1 plus x squared plus arctangent x. Alright, so what if I was asked to evaluate the integral of arctangent x over 1 plus x squared? So I look at this and I see this 1 over 1 plus x squared. I say, well, that sounds familiar. That is a derivative of what's on top. So if I let u equal arctangent x, I know that du is 1 over 1 plus x squared dx. And I've got that 1 over 1 plus x squared dx. So then this integral, after substitution, becomes the integral of u du, which is then 1/2 u squared plus a constant, and now substitute back in terms of x. This would be 1/2 tangent inverse x squared plus a constant. Evaluate the integral from 0 to pi over 2 of sine x over 1 plus cosine square x dx. Alright, so let's see. I know that the derivative of sine is cosine But then if I replace the sign with u, I would have a du squared. That's just messy. But what if I let u equal cosine x? If I were to let u equal cosine x, then du would be negative sine x dx. Well, now look at what I have here. Then I would have an integral of, in the denominator, I'd have a 1 plus u squared in the denominator, and I'd almost have a du in the numerator. I just need to throw in a negative here, and then a negative on the outside. And so, that's what I'm going to go with, because now I can write this as, I have to change the limits of integration, but I'd have a negative, I'd have an integral of 1 over 1 plus u squared du. Now let me change the limits of integration. If x equals 0, then u would equal the cosine of 0, which is 1. If x equals pi over 2, then u would equal the cosine of pi over 2, which is 0. So I'm now from u equals 1 to u equals 0. And remember, we don't like that. We want to go from least to greatest. So I can rewrite this integral now as negative, and then throw in another negative, integral from 0 to 1, 1 over 1 plus u squared du. Those two negatives undo each other, and so then I just have antiderivative of 1 plus 1 plus 1 over 1 plus u squared. That's arctangent u from 0 to 1. And so then that's arctangent 1 minus arctangent 0. Arctangent of 1 is pi over 4, the angle whose tangent is 1. Arctangent of 0 is 0, and so then this is just pi over 4. Evaluate the integral of dt over 1 minus 4t squared. Alright, so this is pretty close to one of the forms we already are aware of. That almost looks like, if I could make it look like this, that would go to sine inverse of t. I should say of u. Okay, so, but it's not exactly right. I don't have a 1 minus u squared, I have a 1 minus 4t squared. Wait a second, 4t squared, isn't 4t squared 2t squared? So I'm going to let u equal 2t, then du would be 2 dt. So I need a 2 here, and so then I would need a 1/2 on the outside. And so then this becomes 1/2 the integral of du over the square root of 1 minus u squared. Well, that's the same as 1/2 integral 1 over 1 minus u squared du. So I have 1/2 sine inverse u plus a constant. Going back in terms of t, 1/2 sine inverse 2t plus a constant. Alright, another definite integral here. We have the integral from 0 to root 3 over 4 of dx over 1 plus 16x squared. Now that sort of looks like an arctangent formula, but it doesn't fit quite. Well, let's see. 16x squared, is that a perfect square? Yeah, that's the perfect square for x. So what if I let u equal 4x? Letting u equal 4x, and du is equal to 4 dx. So So I need a 4 here and a 1/4 on the outside. And if u equals 0, I should say if x equals 0, if x equals 0, then u would equal 0. And if x equals root 3 over 4, then u would equal root 3. So then I would have the integral, I'd have 1/4 the integral u equals 0 to u equals root 3 of du over 1 plus u squared. So then I would have 1/4 arctangent u from 0 to root 3. And so that's 1/4 of arctangent root 3 minus arctangent 0. Let's see, arctangent root 3. So if I draw a reference triangle for that, I'd have to put the root 3 here and the 1 here, and so that would give me a 2, solving the triangle, and I recognize that as being at a pi over 3 angle. So 1/4, and let's see, I have a pi over 3, and the arctangent of 0 is 0, and so then we have pi over 12. Evaluate for positive values of a the integral of 1 over the square root of a squared minus x squared dx. Now this almost looks like an arc sine, right? If that was, instead of an a squared, if that was just a 1, then this is a simple exercise. This would be an arc sine. And it's going to turn out this, we can evaluate this in terms of arc sine, we just have to be a little bit more careful with it. We're going to use some fancy algebra and factoring techniques along with some calculus techniques here. Okay, so here's the first thing I'm going to do. I'm going to factor out a common factor within the radical. And you might look at it and say, well, there is no common factor. Well, in a sense there is, because remember, if I could somehow make this a 1, then life would be easy. So what I'm going to do is, I'm going to use some factoring. Alright, so I'm going to rewrite this as the integral of 1 over the square root of, and here's where it gets tricky. I'm going to factor out the a squared. And so I got a squared times 1 minus x squared over a squared dx. Now, using properties of radicals, I can bring that square root of a squared, I can bring that outside the radical, and so I have 1 over a times the square root of 1 minus x squared over a squared dx. Now I'm going to make a substitution. I notice that x squared over a squared is x over a squared. So I'm going to make the substitution. I'm going to let u equal x over a, then du is 1 over a dx. And look at what I have. I have a 1 over a dx. So then this integral, with that substitution, becomes the integral of 1 over the square root of 1 minus u squared du, which is arc sine u plus a constant. And we substitute that. So what this, our end result is that the integral of 1 over the square root of a squared minus x squared dx is arc sine of x over a plus a constant. And this is something that I'm going to ask you to memorize in the next chapter. And so I want to at least show you where it comes from. Here is a similar exercise, and it would be a good idea to try this one out on your own. So now would be a good time to pause and do that. I look at this integral, and it looks almost like an arctangent. But it's not quite right. If I had, instead of an a square, if I had a 1 there, it'd be easy. So I'm going to use a similar technique to what I did last time, in the last exercise. I'm going to use some tricky factoring. So I can factor this as 1 over a squared by 1 plus x squared over a squared dx. Now there's no square root here, so I'm going to leave that a square in the denominator. But again, I notice that I've got this x squared over a squared, and I know that that is x over a squared. So I'll make that substitution. If I let u equal x over a, then du is equal to 1 over a dx. I've got an a squared. So now I'm going to break things up a little bit. Remember that 1 over a squared, I can rewrite that as 1 over a integral 1 over a square root of 1 plus x squared over a squared, not square root, sorry, just 1 plus x squared over a squared dx. And so now look and see that I have the 1 over a dx, which is the du. And so now I have 1 over a integral 1 over 1 plus u squared du. And this is a simple antiderivative. I have 1 over a arctangent u plus a constant. And again, now substituting back, I'd have that the integral of 1 over a squared plus x squared dx is equal to 1 over a arctangent x over a plus a constant. And this is again a formula I'm going to ask you to memorize in the next chapter. All right, that concludes this section on the calculus of inverse trigonometric functions.